Okay. All of you should have out your handouts 34 through 37, where you can see what they are. This is an online assignment that an offline assignment that you've got that will be due a week from today, the 26th. Now, I put an announcement in Blackboard that says which problems you do. You're only going to do 45 out of this total of 108 on the sheets. So I think you definitely want to look at that announcement. I will cover a few of the problems tonight. Then I'll cover a whole lot more then on Wednesday and Thursday. And then you'll have during the weekend to work on them as well. Previews of coming distractions. I will be teaching you a method of factoring that you have never seen before, unless you had a teacher who attended one of the seminars that I taught a few years ago. Because I developed my own system of factoring that's much easier, much more intuitive certainly than the AC method and guess and check, no doubt, and some other methods. Now, you're going to be free to use my method, or you'll be free to use any other method that you're comfortable with, as long as you're correct. Okay. All right. That being said, let's get started on the material for tonight. I hope all of you were able to watch the video okay and do the ALEX okay over the weekend. Actually, the video probably did it almost as good as I could have. A few people caught what I just said.
I just remember, like, you were like, do you remember what was it? Did he explain it okay? Then it was you in the past.
Yeah.
That was
And I referred to myself in third person at one point.
That was funny.
But anyway, okay, now turn to your handout 8. Handout 8 is a condensed version of this sheet. Okay, it goes through the different properties. About the only difference in handout 8 and this one is this one has some examples to go with it. Okay. Now, the first property of exponents, and by the way, I've already taught you some of this already when we were dealing with some other issues. So this should not be the first time you've seen some of this. Okay, so if you're taking two numbers, first of all, let's do a definition. The base, the exponent, okay? Or the base raised to a power of. We might say 2 to the second, 2 to the third, 2 to the fifth, whatever, as an example, okay? By the way, the second power can also be called squared because of length times width being both the same. And the third power can always be called cubed because a cube, you have identical length, width, and height. And when you multiply them out, then they are cubic. Okay, well, enough of that. What this rule says that if you have the same base and you're multiplying two exponential values, that you simply add the two bases. Here's an example of that. B to the second times B to the fourth. Well, according to this rule, we would take 2 plus 4 and get B to the sixth. Well, what if we stretch this thing out? Here's B to the second, B times B. Here's B to the fourth. 1, 2, 3, 4, 5, 6 of them. Okay, so that's how that rule works. Likewise, the division, think about it. What's the opposite of multiplication? Division. How do we multiply? By adding powers. How do we divide? By subtracting powers. Okay? So here's an example. B to the 5th divided by B to the 2nd. That says B to the 5 minus 2 is 3. In other words, this 2 will wipe out 2 of those, leaving 3, which is what this is showing up here. These 2 knock out 2 of those, leaving 1, 2, 3 of them. This I call the power rule. They just call it the power rule. But I like to expound on that just a wee bit. So what it is, anytime you are taking a power to a power, hence power, that's when you actually multiply the powers. And boy, where I'm standing right now, that little black dot is right in the way. Okay, an example, b to the 4th raised to the 2nd power. In other words, this is b to the 4th times b to the 4th, is what that means. Now, 4 times 2 is 8. Here's b to the 4th. Here's b to the 4th. How many of them we got? 8 of them. Power of a product. Okay, the difference here is we have 2 bases that are contained within a single parentheses. And then we have a power behind it. The rule for that says we take this power times the first term, and we also take this power times the second term. Okay? What if you had a third power here? So then you would end up with a to the 3rd, b to the 3rd. Here's the example showing how and what. Now, I need to elaborate on this one just a moment. Okay? Because on this one, the parentheses makes all the difference in the world. If you had that as an alternative, then the answer to this would be a, b to the 3rd. Because that power only applies to the number next to it, unless there's a parenthesis saying it's got to apply to a bunch of stuff. Okay? And that's true no matter how you deal with the parentheses. The thing you got to be real careful about is, if, let's say you had 3x squared, and you did a substitution of x is 3 or 4. Okay, if x equals 4, then 3 times 4 squared, well, only that 4 gets squared, so you would have 3 times 16, in this case, is 48. On the other hand, again, if x is 4, then if we had this problem, 3x squared, if we have that instead, then we would have 3 squared x squared would be our answer. And 3 squared times 4 squared, or 16 here, 9 there, and whatever that multiplies out to be. How much? 144? Okay. So you see, whether there's parentheses or whatever, that power only applies to the variable or the number directly adjacent to it. And that's very important. And sooner or later, probably some of you are going to make the mistake of not catching that. Okay. But yeah, go ahead and turn the light back on. Thank you. Okay, power of a quotient. Now, this one just said if we've got 2 things multiplied and we take the power, it distributes that power to both of them. I mean, that's actually what we're doing. We're distributing that m in this case. Well, likewise, if you had a fraction, whether that be variables or numbers, this distributes to both the numerator and the denominator. And that's what this rule says. Okay? So in this case, if m were 3, then that would give us a to the third over b to the third. And here's the illustration of that. It would mean you're going to take 3 of these multiplied together, which is 3 of the a's, 3 of the b's, or a to the third over b to the third. Okay. So that's just our fundamental rules there. Now, what about definitions? This is the math legalese. I don't know that you need to write this down. I think I've kind of explained it for the most part already. They don't want b, the base, to be a 0. They want it to be something different. Okay? And we're going to define b to the 0 and b to the negative whatever power. Okay, so by definition, b to the 0, it has a value of 1. Why? Any of you ever had a little niece or nephew or whatever that would why like that? Yeah, well, let me show you why. Agreed? Okay. Agreed? Okay. Now it also works for other bases besides 10. They want down. Okay. Here's an example. 5 to the 0 equals 1. X to the 0 is equal to 1. X, Y, Z in parentheses to the 0 power equals 1. Okay. Anything to the 0 power is 1, with one exception, 0 itself, which is 0. Okay. Negative powers. Negative powers, what you do is you take this value, remember, it's actually b over 1. What you do is you take the reciprocal of whatever this is to that positive power. Okay? That's how you get rid of that negative. Just take the reciprocal of whatever the base is. Okay? Well, then according to that rule we had before, we have to take this to the nth power, which 1 to any power is itself, is 1, I mean. And b to the nth power would be b to the n. So that would be our rule there. Here's an example of that. Remember, we would put this over 1. And if you want to physically do that, that's okay. And then you flip it, get rid of the negative power. Now you distribute that 3 to both of these. So 1 to the third is 1 times 1 times 1 is 1. 4 to the third is ultimately 4, 16, 64. Okay. The value of 0, I already told you that. Okay, now, again, let it be a counting number and it be a real number, not 0. From the definition of this, we also get here, notice this, reciprocal, the power changes, okay? Then we distribute that in. You know what? This isn't any different than what we had, except for these disclaimers. What this business right here is saying is that neither the A nor the B can be zero, because you can't have a zero in the denominator here, and you can't have a zero in the denominator here, is what that's telling. Okay, so A and B can be anything except zero in both cases. Here's another example. Okay, we've got this, we flip it here, gives us 7 squared over 3 squared, 49 over 9. That's as far as we need to take it, because it won't reduce. 7 times 7 and 3 times 3. They don't share any common factors. Simplify. This means -2 times -2 times -2 times -2. Now, just the 2's themselves gives you 16. 2, 4, 8, 16. The negatives themselves give you negative times negative is positive, times negative is negative, times negative is. Remember the rule I told you earlier about if you're taking a negative to an even power, it's positive? Okay, well, that's what that's doing. Now, in this case, that 4 applies to both of these thanks to the parentheses. If there were no parentheses, then the answer would be -16. If there were no parentheses, because you would only raise this to 4 or to 16, and then you'd still have that negative out front. Maybe they're going to show us an example like that in a moment. Okay, here we go. In this case, that 4 only applies to the 2. Okay. What if you got a pair of them? Well, again, this power, this -4, only applies to that 2, not this. So what we're going to do is we're just going to bring down that negative to the end. So here's that negative right there. Okay. And then we got this business. Well, what are we going to do to that? We're going to make it 1/2 to the 4th, and 1 to the 4th is just 1, so basically 1/2 to the 4th. 2 to the 4th, again, is 16. So, no, just 2 to the 4th is 16, so we've got 1/16. And there's your ultimate answer. What's the answer? 1. 1. Because everything's inside this parentheses, so that 0 power applies to the whole thing. So the answer is just 1. What about this one on the other hand? The answer is going to be -7. Because x to the 0 is 1. We still got this -7 out front that we're just bringing over every time. So then our answer is just simply -7. Okay, what's the answer here? -3 to the 2nd. Does the 2 apply to the negative? Yes, so it's going to become positive. And 3 to the 2nd is 9. So the answer is +9. -3 to the 2nd, no parentheses. -9. -3 to the -2nd. -1/9. Okay, That one makes it negative. This business makes it 1/9. Okay, this one, 1. And that one, -8. Okay. Write the final answer with positives only. Well, what does this thing mean? This could be simplified as x to the 8th over x to the 2nd. Do you see that? I'm going to add these two, and then I'm going to flip 1 over to that power. Okay? Now, take this 2 away from that 8. What do I end up with? And by the way, that's the way I chose scratch work. Just the powers. I would get x to the 6th. Let me show you a different way of working this problem. All 3 of these have the same base, correct?
Yeah.
X to the 3 plus 5 minus 2 power would be the same thing. These 2 are multiplied. That one is divided. Okay. 3 plus 5 is 8 minus 2 is 6. 2 ways to skin the same cat. Use an old-timey phrase. Don't be catty. Okay, there we go. You can see they're doing it that way, but I wanted you to see both ways. Okay, this one. Wait a minute. Did someone say -3rd? Okay. Y to the 3rd. 7 minus 4 is 3. That's the easiest way to do that. Okay. Do I care if you show this step? Yes and no. If it's problems specifically on simplifying exponents, yes. Now, when we're using this in other stuff, no. Okay. It's kind of like when we were doing integers, I wanted you to physically show the positive in front of every number that was positive, but later on, I don't care. Similar sort of a thing. Okay, what about this one?
That's 1 over e to the 10th.
Well, there's a couple of ways you can do this one. Yes, and that is the correct answer, by the way. What do? We multiply the power, right? And we got -10. I suppose if you wanted to, you could have made this 1 over e to the 2nd to the 5th. 1 to the 5th is still just 1. And this would be b to the 10th or b to the -10th. You can go backwards with this thing too. Okay, you can close, if you make this, if you flip this, then you got to put the negative on. Okay, there's some more tryouts. 7, 8, 5. W to the 5th. 11 minus 6 is 5, so t to the 5th. You get a -8 there. So 1 over p to the 8th. Or p to the -8, either way, yes.
So if you go back to the one of the 3 W's.
Here.
Yes. If there's no exponent, is that always a 1?
If there is no exponent shown, there is a hidden one, positive one exponent. Always. That was in that PowerPoint I showed you the very first night with oil and water. It was one of the little rules at the beginning of that.
Okay.
Okay, let's go on. Here. Well, oh, that's a minus. And this. Okay. Well,
So if you go, what in the world, that's bad.
what it is at first, I saw that, and it is a minus, but what I saw was an equal sign.
Oh, yeah.
And I thought, well, I'm not going to tell you the words that I thought, but they start with what the, and we'll leave it at that. Yeah, right? Okay, so anyway, what do we deal with that? We got three different bases. So all of those rules I showed you before are out the window. You treat each one of these bases totally separate, and then subtract and add them. Okay, so here we change this to 5 to the third, which is 5, 25, 125. We flip that and get 1/2 to the second, which is 1/4 minus 1/4. And that's going to just be 1. So this thing simplifies down to 125 minus 1/4 plus 1. Well, 125 plus 1 is 126 minus 1/4 gives us 125 3/4. Did you follow me there? Okay. Guess I ought to click it. Oh, if you want to play the common denominator game, you could do it that way and get that thing. And you divide this number by that, and you get 125 3/4.
Oh, no.
Because you have, it's defined common denominator, you have to.
Define a common denominator, okay? I've got to multiply this by 4 and multiply this by 4 and multiply that by 4, okay? Well, let's see, that was 1/2, right? No, it was 1/4 to start with. So anyway, this one's already got a denominator of 4. That one we make into 4/4. This one we make multiply by 4 so we can have it over 4, and it becomes 500. Okay, then you add those up and you get to 503. This is the hard way on this one. Okay, do it the smart way. Okay, another one. We got different bases. That one becomes 3/2. This one becomes 1/4. That one becomes just 1. Okay, so I guess I got to work this one on my own. Using more contrasty pen. So I've got 3/2 plus 1/4 minus 1/1. Least common denominator is 4. Okay, so I'll multiply this by 2/2. I don't have to multiply that one by anything, and I have to multiply this one by 4/4. After doing that, I get 6/4 plus 1/4 minus 4/4. I've got common denominator. Technically, I would change it to this. I don't require you to show that step. And anyway, 6 and 1, 7 minus 4 is 3. End up with 3/4. Okay. Are you starting to feel somewhat comfortable with these yet? Okay, then I'll let you have one like this.
Oh, God. Never mind.
I'm glad you said yes. Right now, you cannot factor anything on this one and that one. You know why? Because you got those critters on the outside. So we have to deal with those two before we deal with what's internal. Okay? So, 2 to the third, I'm taking every term in here and raising it times 3. Using the power rule. The power rule times the 2 gives me 2 to the third. Times the 7 gives me 21. Times the -4 gives me -12. Likewise in the denominator. Times the 4 gives me that. Times the A gives me that. And times this gives me this. Okay? Now, that is 8. That's what it is, and that's what it is. That is 16, and so on. Okay, so that's all we've done so far, is we just evaluated those two numbers. Now we're ready to deal with these. What we need to do is deal probably with these two negatives next. At least that's what I would do. I would not do it this way. I know what they're doing, but I would not do it this way. The way I would do this problem is I would come over here and I would say equals 8 a to the 21st over b to the 12th. In other words, I deal with that. Okay. And then here I've got the 16 and the a to the 6th. And if I flip that, that takes this b to the 4th up there. In other words, these two, you're just going to flip because of the negatives. And the rest of this stuff is going to stay the same for now. Okay, now then, we're ready to start canceling where we can. Okay. Well, what canceling can we do? 8 goes into 8 once, 8 goes into 16 twice. Now let's deal with the A's. 21 minus 6 is 15. So I've used up all of that one, and I now have a 15th power here. Okay, what about the B's? I'm going to use up all of this one, canceling out 4 of those. So I now have 8 of those. Okay, does what I did here make sense to you?
So,
Okay.
could you also do it lining up?
Well, it would be better, easier, if I had the 8 over 16 and I had the a to the 21st over a to the 6th. And I had the b to the 4th over b to the 12th. Now, if I had it like that, is it easier to see? Lesson learned. Lesson learned. Okay. So in this case, it's obvious this reduces to 1/2. Then here, you knock out these 6, which knocks this down to 15 of them. And here you knock out all of these, and knocks this down to 8 of them. So what have we got left? We've got 1 times a to the 15th times 1 again. So all we got left in the numerator is a to the 15th. Because this became 1 and that became 1. Over, we got a 2 here. There's a 1. And we got a b to the 12th. Or 8th, I mean. So this would be your answer. Okay.
Would it be wrong if we left the one in front of it?
Say what?
Would you have it wrong if we left the one in front of it?
No, it's not wrong. It's not in simplest form, but it's not wrong. Okay. Alex might or might not dock you. Likewise me. True, but not right. Okay, well, here they're going at it and doing basically the same thing. Okay, there's another one. What do we got to do? We got to deal with these two powers first. We're not going to work this one. We're going to keep going. Oh, you want it to work? Nobody? Anybody? Okay. So you can have this one instead. You guys try this one. Try this one on some scratch paper. Now, they give you an extra set of instructions here. That's a final step kind of a thing. Well, let's see what this one comes out. Let's see that I messed up my slide over here. There it is. You guys got to see the answer already. Unless you didn't realize what you were looking at. Well, what are we gonna do with this thing? This stuff's all out front. We can flip all of this. Okay? That negative will flip this whole thing. Okay? So just doing that alone, we got 4x y to the negative third times 3x to the fifth y to the second over 8x squared all to the second. Now we can use the power rule with this too. So we'll just bring down this stuff in front for the moment. And then that gives us 3 squared is 9. Okay, that gives me x to the 10th, y to the 4th, over 64. You know, the Beatles came out with a song, Will You Still Love Me, one of 64. Except I'm way past that. Okay, and here we get x to the 4th. Okay, so we've got that simplified down to that so far. Now, we could, if we wanted to, string all of this stuff in one line all over that. Like 4 times 9. Now the x's times x times x to the 10th. Whoops. X to the 10th times y to the negative third times y to the 4th. All over 64x to the 4th. Well, 4 times 9 is 36. X times x to the 10th is x to the 11th. Y to the negative third times y to the 4th is y to the 1st. All over 64x to the 4th. Come this way. Okay, so I got this, I'm just going to rewrite it first. Okay, now, what can I do to these? What canceling can I do? Well, obviously 4 goes into both of these, right? Okay, so 4 goes into this one 16 times. 4 goes into this one 9 times. Now, 9/16 won't reduce, so I might as well go ahead and bring it down. Now, the x's, 11 minus 4 is 7. X to the 7th. Okay. And the y, we just bring down. There's your answer.
Would it all be over 16 now?
Well, I mean, I can write it this way, or I can write it this way, 9x to the 7th, y all over 16. These two answers are the same thing. Okay, either one is equally good. Yes.
So why wouldn't y to the negative third be under the 4x?
Where?
outside of 1%.
because I never converted it.
We just moved it over.
I took this y to the third times that y to the fourth, and I used the subtraction 4 minus 3, or 4 plus -3, if you please, equals 1.
Okay, so,
So I didn't have to, is why I did it. I could have, but it would have made the problem more complicated. You're asking me, instead of leaving that right there, could I have changed this to this?
mhm,
Same thing, more work,
okay,
okay?
so even if we did it, still.
Yeah.
With the same answer.
Yeah, you still get the same answer. I'm gonna erase this because the other way is better. What did I have here? Y to the -3. Okay, questions on this one? How many of you were successful on this one or even close? Oh, that's scary. What if I gave you another one almost like it? Think you could do better this time?
Bring back those 99.
Well, there's their work. No, it's funny you see they got the same thing I got. Okay, here's another one. Actually, this one's almost just like the last one. I'm gonna go ahead and start working this one because I don't have the slides for the answer on this one. Now, does everybody see what I did here? Okay, I basically decided to go ahead and flip that. I wouldn't have had to, I could have continued working this without doing that. Maybe I should. We'll go ahead and put this M to the -6 here. But
I'm not supposed to keep the 3 on the bottom as well.
did I forget something?
Wasn't it
Oh,
27?
27. Thank you, thank you, thank you. Thank you, thank you, thank you. Man, I'd hate to go all the way to the end of this thing and have a mistake and have to go back through every step and see. Okay, so anyway, we got this. Any other mistakes that I made? No? Okay, well, let's start working with this. Let's clean this up a little bit, equals -9 times 64 times m to the 5th times t to the 1st times t to the 18th. Now, you wouldn't necessarily have to show this step that I'm doing right this minute of ordering that, but it might be useful. Okay, well, I'm not gonna do this yet because I'm gonna be able to cancel some stuff there. Okay? Fact is, why don't I just do that right now? Cancel this 9 once, 3 times. Okay? So then I now have -64 m to the 5th t to the 19th t to the 19th over 3 m to the -6th t to the 9th. These two won't do anything, so I'm going to have a -64 over 3 for the numbers. Okay. Now let's deal with the m's. I'm dividing, so I'm going to subtract powers, right? My think scratch word is m to the 5 minus -6. Because we're dividing this one by that one, we subtract powers. And so this becomes m to the, yeah, because those two negatives cancel each other out. And we get m to the +11th. Okay, so we've dealt with the m's. Now let's deal with the t's. 19 minus 9 is 10, t to the 10. That's it. Question? No? Light bulb? Okay, light bulbs are good. Anyone need me to put that back for another moment? Okay, yes, I need to erase it. I've got to be real careful right in here because there's a hot spot on the video that a reflection off the brightness of the bulb that wipes out just about everything. There we go. All right, which brings us to our next section. Addition and subtraction of polynomials and polynomials functions. Okay, what the heck are polynomials? Ever heard of the Polynesian Islands? What does that mean? What does Polynesian Islands mean? It means many islands. Yeah, poly, many. This means many parts. Okay. So far, we've been dealing with first and second degree equations for the most part, with just first power x's, y's, z's, whatever, and maybe a few second power x, y, z's when we're dealing with equations. Now we're going to start dealing with bigger equations. Okay. Now, don't let that word function scare you either. Function is just another fancy word for specialized equation. And I'll talk to you about the specialization in a moment. Okay, so here's where we're headed this. What was that? I need to put that in English, don't I?
Yes.
Okay. Finite sum of terms of the form ax to the n. That's all that's saying. A polynomial is just made up of a whole bunch of these pieces of decreasing powers of x. Powers of x. And numbers that are times x, which we call coefficients, by the way. Okay, that's all this means. Now, more particularly for right now, we're going to be dealing more with equations that look like that one. Okay. And then we'll sooner or later get to the others. Okay, now, this kind of repeats what I just said. The number in front of the variable is called the coefficient. And that n represents whatever power the degree of the equation. Okay? Meaning the highest power. So here we go. In this, 3 is the coefficient, 5 is the degree of the equation. I think you've heard me use first degree and second degree in my language previous. Okay. Here, x to the 14th, there's a hidden 1 in that thing. So 1 is the coefficient, 14 is the degree. Just 7. Look at this. Look at this. Remember that whole string I wrote out there, and I just had that 1 on the end? Technically, that's 1x to the 0 power. But what is anything to the 0 power? So is 1 times 1 is just 1. Okay. If there was a 7 on the very end, then that would be a 1 times for the x to the 0 times 7, or just 7. Now, for right now, that's not too important. But later on, it will become. Okay. Okay, this one, 1/2 is the coefficient, and 1, that hidden first power, is the degree. Okay. If it has exactly 1 term, it's called a monomial. Okay. What? It's called a monomial. Okay. Comes from the Latin mon, meaning 1. Okay. 2-term polynomial is called a binomial, like a bicycle. A 3-term polynomial is called a trinomial, like a tricycle. A 4th degree, technically we could call it a quadrinomial, and a 5th a quintinomial, and a 6th a sextinomial, and a septinomial, and an octinomial, a nonanomial, and a decanomial, but we don't. Thank goodness, because now I'm out of breath. So anything above 3, we just pretty much call polynomial. It's got a bunch. Okay. Now, descending order. That means starting with the highest power of x, working your way down to the lowest. You notice I went 6, 5, 4, 3, 2, 1, 0. Oops, I didn't put the x to the 0. But anyway, descending is called highest power down to the lowest. Okay, the first term in the entire expression, no matter how long it is always called the leading term. Okay, and the leading term also has the leading coefficient, meaning the first numeral in the problem. Okay, so that's just some language right there, and you'll hear me using it throughout. Okay, the degree of the polynomial is the greatest degree of all of its terms. So what was the degree of that big long-winded thing I put up on the board a while ago? 6. So it would be considered a 6th degree equation. Okay, when I erased it back to 9x squared plus whatever it was, then it becomes a 2nd degree. Square, 2 power, 2nd degree. Okay. We will be studying 2nd degree equations a lot. They are also called quadratics. Okay, quadratics, those things you have to factor. And they also create arches or jump ropes. Okay, seriously, that's their generic shape for 2nd degree equations. By the way, all of the different degrees of equations have their own characteristic shapes. Okay, a 9th degree equation is going to look like a sine wave. You know, when you flick a fiddle string and it goes. Okay, well, in fact, any odd degree will do that, except 1. Okay, even degree equations always finish with both ends either up or both ends either down. If it's an even degree polynomial, always. Now, what makes the difference whether they're both up or they're both down? The sign of the leading term. That number in the very first, I have a -11 over here in front of that x to the 6th. So then that means that that one would be going like this. Now, let me give you a little hint. Even degree. Either both up or both down, right? If the leading term is positive, then they're both going to go up both ends. And there could be all kinds of bumps in the middle. If the leading term is negative, then both of the ends will go down. Always. Now here's the way to think about that. Okay? Both up. It will positively hold water. Negative, won't hold water. Okay? You got that concept? Easy, right? Okay. Glad I didn't have water in that. Otherwise, I might be making a mess like I did when my Coke tumped over, the lid came off, and I dumped all 32 ounces in the floor the other night before it was. I was down on my hands and knees cleaning it up with paper towels. You know, I told you guys you make a mess, you clean it. Applies to me too. Okay, ooh, what do we got here? What's the highest power of x?
4.
The 4. What's the highest power of y?
3.
And the highest power of z?
7.
Let's see what they do with this. because these are multiplied, not added, because these are multiplied, the degree of this expression is 4, 7, 8. Okay? You have to add the powers if they are multiplied in turn. Now, so the highest power, the degree of this expression is an 8. What's the degree of this expression? 3, 5, 12. So actually, this one is a higher degree than that one. Well, what about this one? 3. And what about this one? 0. That hidden next to the 0. Okay. Okay, now let's add some polynomials. You remember that expression writing handout we did like first or second night? Where you did W plus 5 and the sum of W and 5, that kind of stuff. This is kind of like that. The square of the sum of X and Y, or written quantity squared. Here's the sum of X and Y, and here we are squaring it. And there are 2 ways, 2 or 3 ways I could describe that value to you if you were going to need to know it from me. I could call it quantity X plus Y squared. If I say the word quantity, that means that's cloistering a group of stuff. And then we're going to have it to some power. Maybe or maybe not. Okay. I could just say parentheses X plus Y quantity squared, probably. Okay. So anyway, that's just some ways you can say that. Now, this one is very different from that one. This one, we would have to multiply out X plus Y times X plus Y and get a long-winded answer, which we've done before. This one is okay just like it is. It won't simplify because those are unlike terms. Okay, so you just got simply X squared plus Y squared. Now you could call this the sum of the squares of X and Y. Notice here we said the square of the sum. Here we said the sum of the squares. The difference in that language makes a difference. Okay, in this, 3x squared, that's the simplest way to say that quantity 3x squared, so that you know the 3 is inside the parentheses as well as the x. Because if I just said 3x squared, that square would only apply to the x. But if I say quantity 3x squared, then I know I've got to square the 3, get 9, and square the x, get x squared. Okay, or you can do it this way: square the product, meaning these 2 things multiplied together, of 3 and x. So this is kind of an advanced writing expressions compared to what we had before. Okay, add these. What do you think? Time out, stop. I didn't. That was not a command for you to physically do it. Yeah. Sorry about that. I want to do some explaining first. We can't combine these 3 terms. Since they're to different powers, they are unlike terms. Now, we can add this one and that one together. And we can add this one and that one together. And that's in fact what we do. So in other words, cubes with cubes, squares with squares, first powers with first powers, numbers with numbers. That's the rule. Okay? So here, they're just grouping the different powers together is all they did here. Okay? This one and that one gives you a total of 4t cubed. This one, you just bring it down, and these two you combine into 11t, or negative 11t. So that's all it is. What about these? Well, now you got to maybe play the common denominator here. By power, not for the whole thing. By power. Do we have any common terms? Squares and squares. They both have a 3 in the denominator. 2 and 3 is 6. 2 and 4 is 6, So we get 6 over 3 w squared. Are you following me? Which simplifies to 2x w squared. Okay, now we'll deal with this one. A negative 1 of these, positive 8 of those gives you 7 of those. Okay, here we got a different common denominator, so we got to change this to 2/8. Okay, you with me on that? So 1/8 minus 2/8 gives me a negative 1/8. Now, honestly, I don't care if you show me that step, as long as you give me this one. Okay. And it simplifies to what we worked out. Optimals. Start the block up.
How about that? I hear your voice changing. So.
Can you?
A little bit.
For about 3 seconds, I thought that was another deviation.
You thought what?
I thought you pulled that out of your nose.
No, no. I blew something out, but I didn't pull that out of my nose. That was bad.
It just comes out.
Okay. Okay, here's another one. A couple of them. I'm gonna skip those two. I want to get just a little bit more done before we get finished. Okay, what about this one? Is there anything I can combine?
Yeah.
I can combine the a square b's, can't I? So I got 7 of them, or 6 of them.
Yeah.
I can combine the a b's and get 5 of them. And I can combine the numbers and get negative 1 of them. Well, what they're doing here, this is just a different way of showing it. Instead of stringing it out on all one line, they lined up the common terms to make it a little easier. And very frankly, I kind of endorse this. But you don't have to. If you got them all stringed out, you got to kind of check them off as you use them up, so you don't leave out something. Anyway, you get this thing. Question? Say again?
You can do that on all of them. if you want.
Well, I'm going to say most. I'm not going to say all. That's a dangerous word. But definitely most, you can do it that way on most. Fact is, in a little bit, when we start multiplying binomials, you'll see that I consistently do that. Okay, here's another one. It's basically what we did before. Now let's subtract them. Only difference is we got to be a little bit more careful. Okay, don't freak out at this. Sometimes we got a problem that has a minus in the middle. And if you have a minus in the middle of a problem, and let's say you got some more stuff up here. What you got to do with this is you've got to distribute that negative, which would give you this. Okay? As a negative times, well, actually, they didn't. They're just saying that this statement is the opposite of that statement because of this, is what this is saying.
Yeah.
I'm jumping ahead to something else. Okay, now, this in simplified form becomes that. That's what I meant when I put it up there at first. Okay, where we distribute this to here, we distribute this to there, and we distribute this to there. Okay, find the opposite of all of this. Well, put it in a parentheses and put a negative out in front. Okay, just take everything that was up there, put it in parentheses and put a negative out front, and you got the opposite of it. Okay, think about it. What if all I had was the number 3? I want to know the opposite of it. -3. Well, put the parentheses around this. What is the opposite of it? Negative that. Okay, now, they haven't asked us to distribute it yet. Eventually, they would. Here, you distribute that negative to each term, and ultimately, that's what you would come up with. This and that are both the opposite of this one up here. Now, let's make this faster. What is the opposite of this? Just change every sign. Boom, boom, boom. Okay, find the opposite. We can go up. All this is saying is something you've already learned. As long as you add or subtract the same thing to both sides, you're okay. That's all that's saying. So what if I got a problem like this one? I got a problem. It's got a minus in the middle. I can't just combine this 3x squared and that 4x squared because I got that minus out here. So to work this problem, they probably got it done for me. They take this minus and they multiply -1 times every term there. Change that to a plus. Change the sign of everything inside is ultimately what you do. Okay. Now, because I've got a plus there between these two parentheses, I can just combine the various like terms. Okay, these two are my squares, here are my x's, there are my numbers. They just clustered them. I don't really care if you write it out in order like that. Very frankly, how would I do it? I would say, okay, I got 3x squared and I got -4x squared. That gives me this one. But I would put a little check mark on both of them to show me that I've used them up. Then I would come to my x's. I got 2 of them here. I got 7 of them there. Makes 9 of them. 9 of them. Then I would come to my numbers. I got a -2 and a -5. Gives me a -7 of them. Okay. That's how I do it. And I actually do make little check marks like that so I don't accidentally miss a term. Yep, that's exactly what it is. Error reduction. Hopefully. Well, here's another one. You guys do this one. This may be the last problem we work tonight. Probably will be. Let me get my scribbles out of the way.
What is that last number?
3. Yeah, well, there's a ball of it right there. And hopefully this is underneath the ball. Actually, it's off to the side of it. The real ball is right here. Okay. You can really see it on my computer screen. Okay, now, so all of that, I dealt with the minus in the middle by changing the sign of everything behind. Okay? Now I can combine like terms. I've got a squares here, and here gives me 9a squared. I've got a's here, gives me negative 4a. And I got no numbers over here, minus 3, done. Okay. With that, I'll see you tomorrow night.
Yeah, at the end of your module, it's gonna have a knowledge check. FYI, and you only have 24 hours to do it.
I
Once
saw
you
that.
finish your module.
Seriously?
When you finish your Alex module this week, you will have a knowledge check and you have 24 hours.
Is Leslie or Candace here?
No. You did the first one, but yeah. I already gave you a knowledge check?
Yeah.
I got one with this last one. I didn't get one with this
Well, I didn't go ahead and do a knowledge check.
Oh, by the way, I put a pacing guide, which is basically my lesson plan, in the course materials
On Blackboard.
folder in Blackboard. You can look at it, and you can basically see what I'm gonna do in any given night. Also, when assignments are due and tests are due and stuff like that. Okay, I had better turn this off.